Welcome to our Math 154 videos. Here we're going to talk about L'Hopital's rule, which is used to evaluate limits of indeterminate forms. So I have a bunch of indeterminate forms listed up here, and for the type infinity over infinity or 0 over 0, we can apply L'Hopital's rule. When we encounter all these other indeterminate forms, like a product or a difference, we're going to need to manipulate it in order to get it to look like infinity over infinity or 0 over 0. These indeterminate powers over here are going to be also manipulated, but we're going to do that by taking the natural log of the limit first. Okay, we're going to take the natural log of the limit first, and then we can evaluate the limit. Then afterwards, we can take the exponential and get back to our original answer. So that's going to be the strategy here. We're going to look at this first example, which is going to be a type infinity over infinity, and then next we'll see one of the indeterminate powers. So for this first example, as x approaches infinity, we can see the numerator is going to approach infinity. As x approaches infinity, the denominator, well, let's look at that. So 1 plus 2e to the x. As x approaches infinity, e to the x approaches infinity. So then we have the natural log of infinity. And as the natural log approaches infinity, we also go to infinity. So this is a type infinity over infinity. Now what L'Hopital's rule says is we can take the derivative of both the top and the bottom separately, and that limit is going to be equal to our original limit. So the derivative of our numerator, x, is going to be 1. Notice it's not the quotient rule. Alright, it's not the quotient rule. We're taking the derivative of the top and the bottom separately. So now the derivative of the bottom. Well, we're going to take first the natural log, so that's 1 over 1 plus 2e to the x. And then we're going to multiply that by the derivative of what's inside because we have a chain rule here. And so that's 2e to the x. So that leaves us with the limit as x approaches infinity. Well, we're going to have on the numerator now this 1 plus 2e to the x. That's just if we flip this fraction up. And then that's going to be over 2e to the x. Alright, now let's see what we have again. As x approaches infinity, 2e to the x goes to infinity. So both the numerator and the denominator go to infinity. So we have infinity over infinity again. Alright, and actually I'm going to use this L prime h here to denote that we've actually used L'Hopital's rule in that step. So since we have infinity over infinity, we're going to need to do that again. So you can do L'Hopital's rule a few times, and that's okay. It's still not going to change our limit. So the derivative of the top, well, the 1 has a derivative of 0. So the derivative of 2e to the x is 2e to the x. And we get the same thing for the denominator. So this becomes the limit as x approaches infinity. Well, something divided by itself is 1. Now the limit as x approaches infinity of a constant is just going to be that constant. So now we've found the limit by using L'Hopital's rule. So here's our second example, and we have x raised to the x squared. Alright, and we're going to take the limit as x approaches 0 from the right of this. Now you'll notice if we plug in 0 here, we get 0 to the 0, which is one of our indeterminate forms, and that's one where we're going to need to take the natural log of the limit. So what I like to do is I like to call this y, whatever we're taking the limit of. That way when we take the limit of the natural log, we can keep track of it, and that's going to be the natural log. We're going to do it over here. The natural log of x to the x squared is actually x squared times the natural log of x, right? Because we can take the power down like that when we have a natural log. So we're going to get the limit as x approaches 0 plus of x squared times the natural log of x. Alright, now we need to see what this is as x approaches 0. Well, as x approaches 0 from the right, x squared goes to 0, and as natural log of x approaches 0 from the right, x goes to negative infinity. So now we have a type infinity times 0, and we're going to need to manipulate this to look like infinity over infinity or 0 over 0. Now, a really good strategy is I would not ever put natural log in the bottom because we don't want to have to take the derivative of 1 over natural log of the x. So we're going to want to rewrite this as the natural log of x over x to the negative 2. Alright? So that way we brought our x squared into the bottom, but by adding that negative in the exponent, we're not changing the actual problem. Okay, so this is still the same thing. Now as x approaches 0 from the right, this is going to be infinity over infinity. So now we can apply L'Hopital's rule. So we're going to get the limit as x approaches 0 from the right. And now notice it's from the right because when we took the natural log, we can't take the limit as x approaches 0 from the left because natural log of x is not defined there. So that's why we have approaching 0 from the right in our original problem. It's pretty important. So now we're going to go ahead and do L'Hopital's rule. The derivative of the top is 1 over x. Alright, because that's just natural log of x. The derivative of the bottom is negative 2x to the negative 3 by the power rule. And so that's all going to simplify. So we can write that as negative 1 over 2. And then we have a 1 over x. And then an x cubed if we bring this x to the negative 3 back up. So one of those x's is going to cancel out. And make sure we don't forget our limit sign because we haven't taken the limit quite yet. So we'll get the limit as x approaches 0 of negative 1/2 x squared. And when we plug in 0 there, we get 0. Now notice that was only the limit of the natural log of what we wanted. So for the actual limit of y, which was our original function in there, x to the x squared, we need to raise our answer in an exponential form. So now we get 1. And that's going to be our final answer for the limit using L'Hopital's rule.